surface forces are an important aspect of the interaction between two or more molecules or two or more bodies. In general classical mechanics, we can see the example of the importance of surfaces. That is, for example, friction. If there is no friction, we won't be able to walk on earth. If there is no friction, we won't be able to stop our car, right, to come to a stop. So the friction, the study of frictions is called tribology. The study of frictions is a very another important aspect of properties related to surfaces, where the role of surface is very important. That field is called tribology, right, in which frictions between surfaces are studied. Similarly, if we go to the chemical side, all the reactions, chemical reactions, take place at the surfaces, right? So, surfaces are very important at the macro scale and at the micro scale and at the nano scale. You know, may have seen a lizard walking on the wall and walking on the floor, the roof, right? That is made possible with the forces of attraction at the nano level, right? So at the nano level, and this means that at the molecular level, right, forces are also very important between surfaces. So we will start from the very molecules or atoms to know it from the origin, and we will develop it from the nano to the macro and then to the normal bodies, right? So let us today do the nature of forces and write a general equation for forces or for energy. We will sometime call forces, sometime call energy, but they are the same thing because force is equal to gradient of potential energy, and potential energy is equal to integral of force. So they will be the same thing. We may sometimes say energy, sometimes we might be saying forces, but that will mean the same thing, right? So long range and short range forces. Right? So suppose we have a collection of particles. We have what? A collection of small particles. We have a collection of small particles, right? And of size, suppose the size of the particle, this is sigma. Right? We have a bunch of particles and each of size sigma, right? And suppose L is equal to the separation between a general separation between particles. Distance between particles, right? Okay. So let us find out what is the energy of this body. Right? It's something. Suppose you have something like this. You know, there are particles, small particles. And suppose this is like L, and the size of each particle is sigma. Suppose we have a system of some particles, right? We want to find the energy of this body. We want to find the energy of this body. Sigma? Okay. So since this system is in the form of a bunch, so we will consider that the energy is attractive, or the forces between them are attractive. So let the energy between these particles obey an inverse sphere, an inverse law, right? And it is something of the form minus c over r to the power n, right? That is a very general form. We don't know what is the form, but we suppose that it is the energy is in some form to the power 1 over r. And with the negative sign, which means attractive, and when it is inversely proportional to r, it means that it decreases with separation. So the basic facts that are included in this equation is the energy decreases with separation, and number second, the energy is attractive. Suppose because this is a system in a collective form. So the total energy, right? This is suppose the energy between two, right, particles. This is the energy between two particles. So if we want to find the total energy, right? Total energy of the system, right? The total energy of the system will be sum of the energy or sometimes we call it interaction as well. Interaction of one particle with all interaction energy, right? The sum of the energy of one particle with R. For example, if we are 4 people, so our whole energy will be my energy with him, plus my energy with you, plus my energy with you. And that will be the total energy of our group. Right? So if we have n particles, that will be like the sum of one particle energy with each of the other one. So if we write it with a big Q, right? If we write it with this is a small W, and if we write that with a big W, right? Then it will be equal to, this is the energy between any two, and if they are n particles, we multiply this with that.
Yes, sir.
So it will be like minus C over R to the power n
So,
multiplied by all of the particles, right?
so,
Yeah, total number of, total number of the particles. Total number of the particles, right? Okay. So we can write this in mathematical form, right? And the total number of the particles can be written as the number of particles per unit volume and integrated with volume.
so,
Number of particles per unit volume
yes,
and then integrated. And that will give you the total number of particles
so,
through all the volume. So it will be like this minus C over R to the power n. And look, that's number of particles per unit volume, if V is the volume, and dV, it is the total number of particles, right? So, let me call this minus C over R to the power n, and let me call this as rho, density, number density, right? Number density, rho. And this dV is equal to 4 pi r squared and to dr. Right? So, now we can take, if the density is constant, 4 pi constant, and C is constant, so I'm taking this out, so that's minus 4 pi, right? And to C and rho, I'm taking them off for confusion. So it will be 1 over r to the power, right? And it will be like r to the power, r to the power n minus 2, which is gonna. Say that?
yes, sir.
And to dr. Right? Okay. And look, what are the limits of integration? So the limit of integration actually starts from, that is the separation. So it starts from sigma, because sigma is the size of the particle. So we cannot integrate inside the size of the particle, because this is the separation. So it starts from sigma to L. Right? The limits of integration starts from sigma to
Yeah.
the minimum distance is the sigma when the two particles will be closely attached to each other, and the maximum distance is some L, which we have considered as the separation. So that is minus 4 pi C into rho. When I integrate this, right?
Yes, sir.
And this, then I put the limit. This I can write this like this: r to the power 2 minus n.
Yes, sir. Yes, sir.
I can write this like what? R to the power 2 minus n. So when we integrate it, we increase the power by 1 and divide by the power obtained.
Yes, sir.
Right?
Yes, sir.
So putting that and then putting the limits,
Yes.
what we get is, right, sigma to the power n minus 3 minus, right, L to the power n minus 6. Divided by n minus 3. Right? And minus 4 pi c rho over n minus 3. And I'm taking this as common. So n minus 3. And that will be 1. And it will be sigma over L to the power n minus 3. Right? That is the equation which gives us the total energy of the body. So, this is constant, this is constant, this is constant. This is constant. Right? The ratio here, what is the ratio? That should be like some constant ratio, for example, for a certain two particles. But here is the case like for n minus 3. So we consider n is integer here, right? Where n is equal to integer, which we don't know. N is the integer that we don't know. It would be like 1, 2, 3, etc. So here, n cannot be 3 here in this case, because here will be 0 and that will be in the, that will be not a finite term. So there are two cases here. Two cases. Either n should be smaller than 3 or n should be greater than 3. There are three possible cases. What are the results from this equation? Our conclusion from one. Conclusion from equation number 1. We have two cases. Either n is greater than 3 or n can be smaller than 3. Our n, which was not known to us, that could be either greater than 3 or smaller. There are examples in both. For example, if it is n is smaller, so the first thing is like if n is smaller, if n is equal to 1, right? So that could be like the gravitational energy, because in gravitational energy, the energy varies as 1 over r. It could be electrostatic energy.
Yes, sir.
With n is equal to 1. In electrostatic energy, the energy varies as 1 over r. But if it is greater than 2, like 4, 5, 6, so one example is with us, the van der Waals force, and that varies as to the power 6. Right? Another is the repulsive force. At very core forces, that's called core force. That varies as 1 over r to the power 12. So that is another example. So there are like two cases, either n can be greater than 3 or n can be smaller. So let us see the two cases, what is the result of them.
N divided by sigma.
N divided by sigma, I think. بالرأس الذي تكتب بها 3 minus n بولي كي وتسمى n minus p كذا
inverse study.
inverse نكو
صحيح.
كويس بيكنا تون ور r تون ور r برا r بوزن minus كذا كنا
Sebenarnya dapat common itu sigma n power n minus 3.
that's the bit that we color will go this way. Right? That's the one word. This word is one word. Huh? Look, that's zero. So one word. Yes. One word. The guru sakana.
Sim.
That's one word. But they will not say about right. That's the key.
Minus.
That's the one.
Yes, sir.
That this is minus two. Or that this is minus two.
صحيح.
Say that.
Sim.
Like don't go off Arabic, right? Don't go that. And but this is a negative sign. For this, a negative sign for the other language. Thank you. Okay. So there are two cases, right? For n greater than 3. For n greater than 3, equation 1 implies, look at this, when n is greater than 3, right? Sigma is a small quantity and n is large. Sigma is the size of the molecule and L is the separation between.
Yes.
So this ratio is very small. So if n is greater than 3, so it could be suppose like 5, suppose it's 5, then 5 minus 3 is 2. So a small quantity to the power 2 is very small. So this can be neglected in comparison with 1. So we can say that 1 minus the small quantity is equal to 1.
Yes.
So we will say that then W will be equal to, right, minus 4 pi C rho over, right, n minus 3 and sigma to the power n minus 3. Right? And that is equation number 2. Right? And for n is equal to 4, 5, 6, and so on. Look at this. We have only the size of the molecules, so these are short range forces.
So,
When n to the power, when n greater than
3.
3, like 4, 5, 6, 7, etc., they will be called short range forces.
Short. Yes.
They are, this describes what? Short range forces. For example, the van der Waals force is a very short range force. معمولين جديا زيادة الوطن دي على بدي اكشن كي كوتش معمول separation زيادة فورا drop key.
Yes, sir.
شسوم the R power زيادة ندم ربع أقطع زي سرا drop key.
Yes, sir.
Short range forces, right? In short range forces, look. In short range forces, contribution from the separation between two particles is not important because it's not here.
Yes.
The size of the particle becomes important. In short range forces, the size of the particle contributes more than the separation between two particles. The smaller is the size of the particle, the stronger will be short range forces. The smaller is the size of the particle,
Stronger.
the stronger will be the short range
Force. Inverse.
forces, right? So the contribution from the size of the particle dominates the separation. No, for the other case, when n is smaller than 3, right? So we can write equation 1 like what? We can write it like W is equal to minus 4 pi C over n minus 3 unto sigma to the power n minus 3,
So,
and I can write it 1 minus 1 over, right? Sigma to the power, and that is n minus 3, right? So, if n is, like we say n is smaller than 1, n is, sorry, smaller than 3, n is smaller than 3. So, here, this is again a small quantity, right? And when this is a small quantity, this thing will be greater than 1.
yes, sir.
Right?
So,
So we can then neglect 1 in comparison to that. We can neglect 1. When we compare 1 and this thing is very big, and 1 is very small. So we neglect 1 then.
so,
So we can write it like 4, 5, right? C rho over n minus 3 and n minus 3. That approximate form of the energy equation
yes, sir.
can be written in this form as well. For n, right, is equal to less than 3. So these are long range forces because here the rho of separation is dominated. Is dominant.
Separation.
The separation is dominant, therefore they are long range forces. The contribution is more from the separation. This equation, the energy is governed by the separation
So,
and not by the size of the particle. So separation means there are long range forces. For example, your electrostatic force, your gravitational force. These are long range forces then. So your electrostatic force is a long range force.
so,
Right? So this was some general discussion about the division of a general equation of energy law into approximate long range and short range forces. Right? Okay. Now let us go a little bit forward.
right.
Now, since we are talking about particles, small particles, right? And their separation, so let us turn toward gases, for example, right? And we write the Boyle's law, suppose, right? So he gave this Boyle's law in 1662, right? And that was P is inversely proportional to the mass. Say, P is inversely proportional to the volume, and this means that when you increase the volume,
Sir.
this will result in decreasing the pressure, right? And if you decrease the volume, the pressure will increase. Say that?
Sir.
So when you decrease the volume means, look at this second number. When you decrease the volume, it means that you are bringing the particles closer.
Sir.
So this looks like it is against the Newton's gravitational law. Because Newton's gravitational law says that more the particles are closer to each other, they should be more attractive. It should not increase, the force between them should not increase. The pressure should not, pressure is force per unit area. What is pressure? Force per unit area. So it means that when you decrease the volume, the pressure increases. Boyle's law says that. Which means that when you decrease the volume, the forces between them are repulsive.
Yes, sir.
Are they, like the pressure increasing, they are increasing. The pressure is, the forces are repulsive, which is against the Newton's law. So that is a paradox with the Newton's law, right? And another ideal case equation, right? That is PV is equal to NR.
So yung the external force apply po, no? Yung the external force apply po, no?
Io podalici cu temperature că mai सही है ना लो मारियो बता क्लोज के दिश सही ना तो टेम्परेचर आ गई तो या चित्त कुर्बानी फोर्स लगे नो दी मीन दे दोबारा मतलब है चित्ता था फोर्स पकार है नो न्यूटन्स लॉ खुदा नो वी कैन अगेंस्ट द न्यूटन्स लॉ रखा सही है ना चित्त वॉल्यूम कैमे हम पकार है चित्त यो बता क्लोज राश दाना चित्त पे से वाले फोर्स लगे that's what पकार ना रखा कौन Say no. PV is equal to RT and RT. That's another equation, and it's called ideal case equations. Right? And for n is equal to 1 Nusra Rashi, PV Nusra Rashi, RT Rashi, but this fails in practical situation. Fails in practical situation. For real cases, it fails. Right? So, for real cases, there was another person, Van der Waals, who give another equation, right? Say that. Therefore, for real cases, for real cases, and that was three plus a for b squared and v minus v is equal to arch. Right? That is the van der Waals equation for real cases. And look, it brings about change in this one. So they replace V by something smaller than V. It subtracts the size of the molecule from here. Replace V by what? V by V minus B,
Yes.
where V is the size of the molecule. So replace V by what?
So,
V minus, subtract the size of the molecule from the actual volume.
value.
Sorry, and then it replaces P by what? P plus A over V square, and this term is actually, this takes the all the forces, right, which are A over V square, forces that are attractive, forces that are attractive, right? For example, we will call the van der Waals forces. Van der Waals forces. This term A over V square this represents the part of the forces which are attractive and which we will call the van der Waals forces. So the correct equation for the real gases is followed by this equation, right? Now, the important stuff here in the domain of forces, this equation is like this equation. There are two differences. V is different, P. V is different by V minus P, and that is the size of the molecule. So we cannot do anything with the size of the molecule, and if we know the size of the molecule, just subtract it from the volume. But the other difference is P by P plus A over V square, which we said this is because of the van der Waals attractive forces. So we don't know this. What is A? So let us know this part of the forces between particles.
Yes.
Now the unknown, what is the unknown? The A over V square. Let us know the wonder wall forces. Let us try to understand the van der Waals forces. Right? For the van der Waals forces, right? Let us see all the factors which can contribute to it. Van der Waals forces, to know van der Waals forces, let us see what can actually be giving rise to this force. What are the factors? What is the origin of this force? So one thing that comes into our mind would be like a charge force.
Sir.
One thing that comes into our mind could be like the Coulomb forces. That comes to our mind, right? Will be the Coulomb forces. Are charge forces. What? Charge forces. Coulomb forces are charge forces. There is one theory, and that is called the field theory, right? The field theory. In the field theory, we suppose that one charge produces a field around it. A charge produces a field around. For example, some Q1 charge is here, and according to field theory is just one picture. It's not real. We don't know it's a picture that we want to understand things through. May not be a real picture. Maybe there is some other picture. But this picture is like it produces a field around the charge, and that field is represented. We represent it by lines.
Yes.
Right? This is the field theory. And then we say if there is another field charge Q2, then this charge interacts with the field of the first charge. This is called the field theory. This charge interacts not with this charge, but with the field here. For example, that is E1. So Q actually interacts with
E1.
Q2 interacts with
Sir.
E1. That's called the field theory. And then we say the force is equal to Q2 multiplied by E1.
E1.
The force on this charge is equal to Q2 multiplied by E1. Where E1 is the field produced by charge 1.
Okay, 1.
Right? So we say the electric field produced by this charge E1 is equal to 1 over 4 pi epsilon naught and epsilon r if we are in a medium. Right? सही था? 1 over r square रह जाएगा ना?
Yes, sir.
Q1.
सही था? And Q1. That is the field, and it should be like some R in it. So that now the force will be like the interaction between this charge and
E1.
E1. The force will be Q2, Q1, and divided by 4 pi epsilon and epsilon r, and 4 r square if I write scalar. सही था क्या नाम?
Yes, sir.
हाँ?
Sir.
Okay. Now if we have a charged body, a charged system R, if we have a charged system R, a charged body, many charges brought together. Right? Then what is the energy stored in this charge body? Energy stored in the body. Suppose only Coulomb force is in action. Look, we are only talking about Coulomb force, no other forces. Charge force. Right? So we know that F is equal to minus gradient of potential, right? Divided by and multiplied by charge, right? Some charge. Right? So, if we take potential energy, then you multiply the two, and that's potential energy, the Q and the V. Right? So, the energy of the charge system, that will be equal to integrating minus F R the forces with the separation, right? From minus infinity to R. You bring, look, starting from the first charge, there is nothing here. So you bring a charge from infinity to this point, which is having some or distance R from the origin. Right? That is your first charge. Then you bring another charge from infinity. Then you bring another charge from infinity. And how much work do you do? Then you bring another. And then you add all the works. Very good, huh?
Yes, sir.
Then you add all the works together. And that gives you the energy of the system. Of the whole body. Right? So W of R will be equal to minus infinity to R, and since this is gravitational, so Q1, Q2 divided by 4 pi epsilon naught epsilon R, and by R square. Thank you. dr. सही ना? And this will become Q1, Q2, 4 pi, epsilon naught, epsilon R, and that over R sheet.
Yes, sir.
Integration A.
Yes,
Yes,
sir.
sir.
Sorry? So if that is question number 1. Now we can say that suppose Q1 is equal to, right? Suppose Q1 is equal to Z and the charge of electron. Z is some number.
Yes, sir.
I can keep call Z1 and Q2 is equal to Z2E. So then this was W R that will be equal to Z1, Z2 and to E square divided by 4 pi epsilon R and over R. This equation gives you the energy of the electrostatic energy of the system.
It's not two charge.
Just from many charges. Because this we have integrated this. The whole body. First,
Yes, sir.
we integrated this. You have integrated from infinity to a position R.
Yes, sir.
Right? Dattam de tapa pimrazi, tapa pimrazi, so the R means Dadayunde, we are down the to the integration for R. So it's the whole body, not two charges, right? So that is the energy, right, of the system of the bodies, right, charged bodies, and look. أغلب الشراء أنا دوا دريش أروح أروح نذيك أروح ذيك absorb Z1 or Z2 كم absorb. See that? So basically in the tool charging of the electron كلام.
Yes, sir.
दाम में यो charge मतलब दाम में चला यो particle है. बहुत
Yes.
case तो सब खत्म.
Yes.
This means this is the whole body in terms of the charge of electrons.